Okay, it's time for phase diagrams. So we discussed the vapor pressure and the trend with respect to temperature. So anytime you measure at various different points of time, if you're able to determine how the pressure varies with temperature, you would generate what are called as phase diagrams. So these are essentially plots or graphs which are combinations of pressure and temperature. Now, a couple things here. In a phase diagram, you would be able to see how exactly the solid phase behaves as compared to the liquid phase or the gas phase as we vary the temperature and as we vary the pressure. Now, if you notice the left hand side, so this segment, let me change the color, that is the solid. The one in the middle is the liquid, and the one in yellow is the gas. What that means is the interface, so the commonality, the curve between, let's say this is 0 to A, 0 to B, and 0 to C. So 0 to A, that curve essentially will have an interface from solid to liquid. So you can also say that this is basically a melting curve, or also sometimes referred to as a fusion curve. Likewise, if you consider liquid to gas, that is where vaporization will take place. So there'll be many vaporization points, and this curve OB is going to be referred to as the vaporization curve, and likewise the OC is going to be my sublimation curve. Also realize the point O, which is where the solid, liquid, and gas meet. That means that is the point where all the three phases coexist. That point is going to be referred to as the triple point. So whatever is the temperature, whatever is the pressure, so for water it happens to be 0.0098 degrees Celsius and about 6.0 times 10 to the negative 3 atmospheres of pressure, that is your triple point. I also want to make a point here that there are many melting points along this OA curve, but at a specific pressure of 1 atmosphere, the melting point that you see is going to be referred to as the normal melting point. And if you extrapolate that 1 atmosphere all the way to the boiling point curve, essentially that point is going to be the normal boiling point. So again, each area signifies the specific phases, whereas the lines are the curves, which is where the phase change is occurring. And specifically at 1 atm, we refer to that particular melting point as the normal melting point. Of course, the entire curve has many melting points on it. Likewise, OB is made up of many vaporization points, but specifically at 1 atm, that particular temperature is going to be called as the normal boiling point. So if somebody asks you that in going from maybe let's say there's a point 1 here and there's a point 2 here, in going from 1 to 2, what kind of process is occurring? You can see that a solid is becoming liquid, and so that process is melting. The opposite of that would be freezing. Likewise, 2 to 3, that would be evaporation or vaporization. 3 to 2 will be condensation. And if somebody asks you 1 to 3, directly, that would mean it's a sublimation process, and 3 to 1 will be a deposition process. Now, as discussed previously, if you want to go from 1 to 2 to 3, so let's say you have ice and you start heating it, essentially ice is going to, so let's say maybe we have 1 and 2, and you want to continue to go to, up to 0.3. You would say that as you increase the temperature, so the ice block is actually increasing in temperature, and it's seeing this rise in temperature till the time that ice basically hits the melting. That is the time when the temperature is not going to rise because a phase transition is taking place. And when all of the ice gets converted into water, that is when the temperature will continue to rise. So again, realize that phase diagrams are nothing but the movement or the change in temperature or pressure and the effect that it has on that particular compound. Another thing that I want to bring to your notice is the supercritical fluid, or SCF, or critical point. Really, this point beyond the point B is where no matter how high the pressure is, essentially you will not be able to convert the gas into the liquid form, and the temperature is so high that no matter what you do past this point of time, the liquid will not be able to get converted into a gas. So this is this mushy region where, if you will, usually whenever you have a liquid, there's this meniscus. But at SCF, essentially that meniscus is lost. So it's like one mush or new phase that is seen, and the temperature at which this occurs is called as the critical temperature. The pressure at which this occurs is going to be called as referred to as critical pressure, and the point itself, together the temperature and pressure comprise the critical point for that particular compound. Now, having a critical point or knowing a critical point is an important thing, because you can actually have improved properties. So as you increase the temperature, essentially you would be able to carry out extractions. So you would be able to have a material which has the property of a liquid, in a sense that it's not very voluminous, but at the same time it's able to, since it's at an elevated temperature, you would be able to extract out chemical compounds. And one application of this is found in food industry to convert caffeine into decaffeinated coffee. That's one application for the supercritical fluid. Now, one thing I would definitely want to say, if we compare the OA curve on this particular curve, which is pointing more on the left hand side, and if I compare that to those of iodine and CO2, in those cases that OA will be more pointing towards the right hand side rather than the left hand side. And so both the fusion curve for CO2 and iodine have positive slopes, and as the temperature increases, the pressure also increases, in contrast to the fusion curve of water, which has a negative slope, in which the as the temperature um, as the temperature decreases, essentially you're going to see an increase in pressure, or not so much increase in pressure. So the fusion curve with the phase diagrams for most substances is usually with a positive slope, and in this case one can say that increasing the pressure essentially favors the denser state. So as you increase the pressure, you are going from a liquid. So as we increase the pressure, a point of time will come where the solid would get converted into a liquid. On the other hand, if your curve kind of looks like that, then, and that is your triple point, such that this is solid, this is liquid, and this is gas. You can say that as you increase from point A to point B, as you increase the pressure, essentially you're going to go from the liquid phase to the solid phase. So essentially you're moving towards the um, the phase which has a greater density. So while for solids, while for CO2 and iodine, that is true. One can say that water is different, and in case of water, it is the liquid water which actually has a greater density as compared to solid water. So one can say that for those substances in which liquid it has a greater density than the solid, you're going to see a negative slope for the OA part. On the other hand, those that have a greater density of solids rather than liquids, those are going to show a positive slope. Now, one thing that I would say that both in case of water as well as in case of iodine, for instance, this liquid phase is essentially considered very stable, and the triple point is kind of all the way down here. In case of CO2, however, that triple point is all the way up, and so essentially as you go from let's say you have a particular component at position 1. As you increase the temperature, it goes from 1 to 2 without having to go through the liquid phase. And in a situation like this, you would say that we have this particular material which will sublime very, very easily. So like I was saying, triple point is the point where all the three phases can coexist. Critical temperature is the temperature above which the gas phase cannot be made to liquefy anymore, while critical pressure is the minimum pressure required to liquefy a gas at its critical temperature. And past that point where the supercritical fluid exists, it's neither a true liquid nor is it a true gas. So at this particular um, um, temperature and pressure, one can say that the supercritical fluid is going to act as a great solvent, and it's going to do so selectively, dissolving a number of compounds. And so a lot of times, like I was talking about SCFs in food industry, carbon dioxide is used as a solvent to extract coffee from coffee beans and convert or generate decaffeinated coffee. And one can say that caffeine dissolves in supercritical CO2, but other substances, those that are responsible for the flavor of coffee, they are retained in the coffee beans. And so, consequently, the caffeine is removed without substantially altering the coffee's flavor. And once the extraction is done, the supercritical carbon dioxide is removed from the mixture by simply lowering the pressure below the critical pressure. And so that will be the point where the carbon dioxide would evaporate away, and hence no residue would would remain in that reaction mixture. Uh, just to kind of put things in perspective, we are supposed to label a solid region, a liquid region, a gas region. Normal boiling point, that means 1 atm, but go all the way over here. So that's normal boiling point. This point will be normal melting point. This guy will be the triple point. Beyond this point, we will have the critical point. So this is the SCF region, where the critical pressure is 260. Critical temperature, you must use a ruler, is beyond this 440 Kelvin or so. And that's how you would label this phase diagram.